Okay, so to continue our process through the Rosenshine Principles in Action Masterclass, I'm going to now focus on the section, the strand sequencing, concepts and modelling. So this is where I'm looking together the principles that where Rosenshine suggests effective teachers know how to present new material using small steps. They provide models for what success will look like and for how to do things. And they'll provide scaffolds to allow students to access higher levels of achievement in various different forms. I'm really keen that teachers see this as completely integrated with ideas about curriculum. So lots of schools are working on thinking about their curriculum, how it's sequenced, and how to develop models and scaffolds. So it's fantastic that Rosenshine's principles and curriculum design are completely integrated in that way, so that you're not doing a separate agenda when you start talking about Rosenshine's principles. You're actually just working out how to enact the curriculum that you're designing, and they go together. So it's always important to use examples, I think, here, because this is a very curriculum specific aspect of Rosenshine's principles. There aren't really any generic things here. They're just subject specific ideas, and the best way to get this across is through giving various examples. An example I often use is this one, because it's something which fascinates me, that students can go through school learning maths without actually really learning it. They're studying it, but they get to the age of 16, you find them in FE colleges retaking maths. They've got a grade 1 or 2 at GCSE, and they still can't do things like this question here, adding fractions. And this idea that you find a common denominator, so that you're actually finding pieces of a fraction that are the same size, so you can count them up and so on. So that manoeuvre there is this. Some students find that incredibly baffling. They want to write something like 3/7 as the answer to that question. And when you probe with them, you realise that when you're saying the word a quarter, 1/4, even saying quarter and 1/4 are not absolutely linked. Some students, when they hear you say a quarter, are not visualising 1/4 of something immediately. Some students, when you say what's bigger, a fifth or a quarter, hear the 5 in fifth and think that must be bigger. So it's not an immediate link that they're making. And the very problem of adding fractions, meaning something to do with combining shapes of different sizes to make one combined unit, and therefore the need to have elements which are the same size, this issue of finding the lowest common multiple and so on. This is quite an abstract idea, and they'll revert to a method which is basically 4 times 3 is 12, which I'm told that's correct, so that's what I always do. And essentially that's what they think they're doing. But students who can't do this really are not just adding fractions, they're doing multiple stages, and it's important as an effective teacher of maths to know what all the stages are. So where are your students getting stuck? Are they struggling with the idea of fractions, equivalent fractions? Do they understand the idea of a common multiple, 3, 6, 9, 12, meeting 4, 8, 12, that kind of thing? And the important thing is to be able to go back to where they're at. And often I find that with teachers, say lower down in Key Stage 3, are making the assumption that the students already know what fractions are, and they're dealing with the operations around adding them, when in fact some of their students don't know what fractions are, even though they've been trying to engage with that idea for several years. So in your curriculum design, you need to be able to go back to where students are, and it may be that you need to introduce or reconnect with equivalent fractions and spend a lot of time forming that schema around what fractions are in some sort of physical model, a number line, and different shapes, and really working hard around that before we start worrying about operations to do with adding fractions. We need to go back to that, and that's something which you have to have. Teaching is always contingent. It's should I go forward, should I go back? And your curriculum knowledge about the building blocks for a coherent schema are really, really key. This is one of the examples I often use. You then need to be able to know how to go forward. So how do I, for example, bridge from the concrete world of counting things and numbers meaning a specific countable amount or a place on a number scale into the abstract world of algebra? And this is something which a colleague once showed me was a useful bridger for introducing algebra and brackets, and I found it very powerful. So in this example, the jar of sweets there has some sweets in it. We don't know how many there are, but we know that there's a certain number which can't change if the lid is on. We could say have 4 extra ones. And if you said, well, let's give the jar plus 4 extra ones to 3 people, then how many would we have altogether? And the brackets then represent this idea of 3 lots of everything in the bracket. But a lot of students lose sight of that. They don't know what the brackets mean later on. And so you'd have to have this thing, always remember what the brackets are, some concrete home for the abstract idea, which students can fall back to when it becomes a little bit obscure and abstract. And that's just one example. So every subject has got its equivalent of that bridging from concrete to abstract. How do we explain ideas in terms of what students already know and can relate to? And that's at the heart of any good explanation. If you can't find something the students can understand in terms of what they already know, then everything you're giving them is not going to stick. It won't make sense. An important idea, and Rosenshine refers to this in his book, he talks about worked out examples. That's the language he uses rather than worked examples, but it's an important finding from studies into cognitive load theory. And in the section on Rosenshine's principles, provide models, he says that worked out examples is another form of modelling that has been used to help students learn how to solve problems in mathematics and science. A worked out example is a step-by-step demonstration of how to perform a task or solve a problem. The presentation of worked out examples begins with the teacher modelling and explaining the steps that can be taken to solve a specific problem. The teacher also identifies and explains the underlying principle for these steps. So that very straightforward idea that teachers are showing what to do step by step. So you might introduce this example here of one particular method of working out the percentage of a number, and then you would show another one. It's important to have more than one. So here we can see the method emerging. It's not specific to the numbers. It's a general method which would apply to any numbers. And then we might do another one. And in this case, we might be able to say to the students, right, well, what would we do next? And we would discuss the method and stand back from it and explore exactly what is happening, making sure they understand the steps. And probably most students will be able to do the next bit. And then you might give them one completely to do on their own. And there the method is much more securely learnt than just showing one example and off you go. And that is a feature of less effective teachers, where Rosenshine identifies is that less effective teachers typically use fewer worked examples, and the students are left to flounder without that solid, secure, the exposition of the examples up front. So, modelling, showing students what to do, and then discussing the underlying principles of what has been done, is an important part of good teaching. Another thing I think in the sequencing concepts of modelling is to have a broad view of what knowledge is. And this is really coming from me rather than from Rosenshine directly. So schema building isn't just about the factual knowledge which the teacher provides. It's a lot of knowledge we gain from experience of things. So the example I often use is the difference between going into some long grass in the summer and using a pooter, which is what that thing is on the left, to collect some insects and then looking at them, studying them, seeing how they move, seeing how they behave, seeing how they vary. That's knowledge which you can't give. That has to be gained by doing it. And then linking that to an abstraction of an insect, labelling the parts, making a general case, and learning words like antenna and abdomen. That's all a connected, integrated schema building experience. Whereas some students, their curriculum doesn't allow for the practical element, so they're told only about the abstraction. We see label diagrams of things, and that's kind of what we're doing. And where children have had that type of learning, my feeling is that their curriculum and their schema building is less likely to stick. And the other side is also true. If we just sort of observe things without learning the language for describing them, then we're also having a thinner curriculum. It's the two together that give you the richness and the depth, which is what we need. A lot of curriculum development is well informed by some fundamental principles. Here's a science example. This comes from a secondary Key Stage 3 attempt to list the main ideas in science that they would probably feed into most lessons where they're relevant. Particles and energy are key to nearly every aspect of science, and so on. Chemical and physical change are key. I've come across teachers, mainly at Key Stage 2, where they're non-specialist, who need to have that fully explored. So, a candle melts. That's a physical change, but it also burns, which is chemical, and it's the burning into and turning into carbon dioxide where the candle disappears. The reason a candle disappears is because it combusts, not because it melts. And that is a key idea which you have to grasp. And there's some fantastic work, for example, this by Christopher Such, who's a brilliant blogger and a writer about primary curriculum. In his school, they have these great lists of what they call the big ideas. Very simple, 3 big ideas for chemistry, physics, biology, and natural sciences. This idea that matter can change if the arrangement of the building blocks change, but that all matter is made of tiny building blocks is a nice simple idea which drives your thinking, and that's a good way of building a schema. I've got tons of examples of these things which I think are useful. In just more science examples here, how you build up an understanding of the phases of the moon. And I like to suggest that teachers take their class outside or do a class tracker. So so children are observing the moon directly with their own eyes, looking at it and being asked to study it with their own eyes, so that it becomes a real thing, not just a visualization of something. We can see the moon regularly throughout the year, and it's quite possible to make that an observable phenomenon rather than something you see via a computer or a textbook. And getting a sense of the scale is important. So you find models for how to make an idea make sense by showing the distance between the Earth and the moon at scale, rather than a false idea of that which confuses people. This idea of the distance being very much larger than the sizes, and that explains how we see the moon as we do. Another really important one is something like this. So how do we get children to understand the link between the macro observable world of solids, liquids and gases, in this case ice, water and steam, with the kind of molecular version, the particle model? And that takes some thinking, and it's just as an example of schema building where students are being taught in a way which makes this link very, very vivid by, for example, handling ice and seeing it melt and pouring water and observing ice floating in water directly and feeling the condensation on the outside of a beaker of icy water. These are things that are going to likely to help make connections which are vivid, real, sort of complex, but also sort of in a well-explained way, identifiable. So yeah, we can, condensation is a thing I have seen and I can relate to. It's not just a word I'm hearing. And you can't overdo that. I think you have to constantly make these links for how the particles behaving, how do they explain what we see with our own eyes. And then that links into a bigger picture thing where you might, for example, do the big world global version of changes of state which we observe through weather, through the water cycle, and applying words like condensation, evaporation to the water cycle is part of that. So this is how an effective schema building happens. Another example would be, say, where we're trying to explain a chemical reaction like this, where there's so many different levels at which we have to understand that there's the observable, which is, a green powder turns into a black powder. There's the words for the chemicals, so there's the language. Then there's the symbolic representation, which helps us see that the atoms are the same atoms just reorganized. And that's a fundamental idea in chemistry, that the atoms we start with are the atoms we end up with, just reorganized and combined in different forms. So knowing that is, and knowing how to make those connections between those different types of knowledge is an important part of sequencing concepts and modelling how they connect. I've encountered students who, for example, are not are not secure in their knowledge that atoms don't change when you do a chemical reaction. So they might, if you ask them what does copper carbonate turn into when you heat it up, they might guess and say something like iron oxide, and you know that if you're a science teacher, that's like a joke. That's impossible. That's like magic. But you know, why don't children think that's ridiculous? It's because they don't really fundamentally understand that the atoms are really unchangeable in chemistry, and clearly that's a misconception which you have to anticipate and then teach up front and make really clear that the atoms can't change. It's always the same ones, and that's actually quite a beautiful and simple idea which it helps understand all kinds of things. Another example which comes from science is this idea of the when do you sequence experiential knowledge with very strongly formal learning. So here you've got an equation which explains the force on a wire in a magnetic field, which is useful to explain how motors behave. If you just get introduced this abstract idea about force B representing magnetic field and this equation, that's a very abstract notion, and a lot of children really struggle with this. They just learn it at a very sort of superficial level because they just are told that it's an equation. They sort of have a vague idea that it's to do with magnets, but their intuition for how it behaves is not good because they haven't really spent any time seeing how these behave in a sort of tacit, sort of physical, real world way. And my feeling is that you do well to plan a curriculum where you understand that introducing ideas in like this, a motor behaving in a certain way, it can be experiential. We can talk about the language of strength, rotational speed, and the orientation of various things, and formalise them later. And students who don't have that dual experience find that their schema is poorer. Either they've not formalised it or they haven't had the concrete, practical, hands-on feeling so that it makes sense. And getting that right is important. And the last example, which comes from science, is this idea of depth. One of the things we're doing when we ask lots of questions in the curriculum is modelling the depth of understanding. So here, you could ask a year 2 class to go and run around the playground, and they were out of breath, and they can feel their heart beating faster, and you can discuss, why that happens. Why are we out of breath and our heart's beating faster? Because we run around. And you 7-year-olds can give you a pretty good answer about that in terms of energy and using their muscles and needing to breathe in air because they think of in those terms. But when you're in year 7 or year 11, the language and depth of knowledge would be greater. And that's something we're modelling. We're pitching the level of depth to our students, and we're planning in our curriculum to revisit these ideas at increasing levels of depth. This kind of spiralling concept. So sequencing concepts is, for me, is important. Links to this modelling of standards and depth. It's a really powerful idea. One of the things I often encourage people to do is to write schemes of learning where the beginning of every unit, you write out what prior knowledge you think students should have before you continue. These are just some examples. But then you actually check that the students do have that knowledge. So if you're about to discuss Ted Hughes' bayonet charge, and whether there's some required knowledge about World War I and trench warfare to understand the poem, really, well, who teaches that? Do you teach it as the English teacher? Are you relying on that knowledge already being there? And if you are, well, are you going to check that they have it before you just plough on hoping they have it? And so on and so on. So identifying the prior knowledge and then checking that students have it, teaching them the bits they don't have, that seems to be an important part of this whole idea. A common thing to lots of teachers is building writing. How do we move from basic writing to sophisticated writing? It's a hugely complicated thing, but we can't just assume that everyone knows it. There's not just some automatic natural maturation which happens, which says students just get better at writing. they can get better at writing through maturity and engaging with language, but most of what they learn is specifically taught. And in order to do that, we have to combine an idea of what what success criteria are. So what are the features of excellent writing? We might make a list of those features if we can identify them, but that's always hard to understand unless you see what those things look like for real. So I'm quite a big fan out of these moderation materials that are produced for Year 6 teachers. As a non-specialist person, these help me understand why writing of a certain standard is considered to be that standard, because the success criteria are used alongside examples and they are annotated very, very clearly. So you can see some features of the writing which then make sense of the success criteria. And it's a bit like, I like to talk about this in my training, the Great British Bake Off, where they have the technical challenge, when they have a line of cakes and the judges, they don't go along the line of cakes deciding, how many marks to award each cake. They just decide which one is the best on taking into account everything about it, and they apply retrospectively some success criteria. They'll say, well, this one is the best because of these reasons, and they'll say, well, this one was the worst for these reasons, and then they'll reorganise the ones in the middle. And sometimes they're making a sort of fairly arbitrary choices there, but it's a judgment. It's not an absolute measure. And essentially that's what a quality model assessment does. And this is one of the main things that we need to be doing when we're modelling. We're modelling standards. This is a primitive painting. How do you make a more sophisticated rainbow painting? Well, it'd be hard to describe that to somebody. You couldn't just say to a child, make a more sophisticated version. You would have to show them what you meant by that. And you can see in this picture that there would be different ways for that to be realised, and showing alternative paths to success can be part of that. So showing examples of excellence, modelling excellence, I think is a really important part of what we mean by modelling. This is what and then from the models, teasing out why we consider them to be more sophisticated or better, or whatever the words we are using. There are reasons, even we might not all agree on them. Here's an example of something I like to share. I love this story. This is a piece of writing I found in my study last summer, my son's own piece of writing, which he did, and the poem, which I always read out in the CPD session. I love that last stanza here. It says, "Nor did I know before sun could make the sea golden like straw turning into gold." So it's fantastic. And when I first found that, I was quite impressed with my son, thinking, wow, you really were a talented young boy, age 7. But then I thought, actually, it was a bit too good to be true. So I Googled it, and I found this poem, which is, well, you can see what's happened. The teacher had given the class Lillian Moore's poem, Until I Saw the Sea, and they had used it as a scaffold for writing the poems of the same structure. And that's fantastic to me. That's a classic example of a teacher setting a high standard, pitching up, being ambitious, and allowing the students to experience that level of excellence by having a go at doing something, showing them that language and takes meaning in the form of the poem. The words are affected by the form in which they're presented, the structure of the poem, and so on. So that to me was really, really fantastic. Of course, you couldn't say that he had learnt to write exceptional poetry at that point. He has just been shown that he can do it with support. He then, of course, would need to go and do that by himself afterwards. So the scaffolding would have to come down for us to be able to say he has learned how to write poems of that standard. So modelling and scaffolding are important, and it can happen at things like this, sentence level structures, like these ones from English at the top there, throughout the novel, at first glance, da da da. Now these are not things which children automatically know how to write. They have to be modelled, shown. You teachers need to show how they work many times. They need to then practice them many times, and eventually those would become part of their repertoire of things they can do. Things like science writing a sentence like, initially the concentration is. Well, students don't naturally use the word initially. They have to be shown that that's a useful, powerful way of conveying the sense of the initial conditions of an experiment. And it's just a simple way of starting a sentence. Initially, boom, boom, boom. And again, you model it, you show how that works. The students can then practice it. And then right up to this type of thing where you've got a GCSE standard essay. How does the student get 8 marks? That's an important question. You can't just show them the criteria. That's a very opaque paragraph sentence. The answer is presented in a coherent narrative account that demonstrates a range of accurate and detailed knowledge. Well, anyone looking at that is begging to know what that would look like in reality. What does one look like? You have to show an example. But you can't just show the example and hope that the meaning is gained. You have to invest significant time discussing the reason why that example is considered to be a full marks answer. And it would be because of various things to do with, for example, there are all we need is 2 main reasons. That's the main thing. 2 reasons. Each one is has an example. For example. And then in each case, this was an international crisis because. This was an international crisis because. So you've got the knowledge of, in this case, Hungary, Khrushchev, what happened in 1956, what Eisenhower did. You've got that whole narrative. But then you've got this issue of why those events made it an international crisis, that concept. And you have to then link it back to the question, giving an example. So there's a lot of modelling going on there. There's modelling of the knowledge content required, the structure of the paragraphs, and the importance of linking back to the question. All of that is modelable. And it's the same at A-level. Here's an example with an essay at A-level, an economics example. And, I've had experience working with departments where, getting the students to understand the features of an exemplary essay took quite a lot of time. And it's not just the superficial listing of lots of factors that was gaining credit. It was in-depth analysis of a few factors which gained credit, and making that distinction evident to students took some thinking. So everything we're doing in writing is modelable. That reading the question, which knowledge they should have, how you sequence ideas, where do you begin, how an individual paragraph works, and then this need of answering the question and not just writing stuff it's writing the relevant things. And all those things are teachable provided you can actually show how it's done, and that modelling aspect is essential. But of course, once you've modelled, the students need to be able to do it independently. So as with stabilisers, you can't really say someone has learnt to do it until they can do it without the help with the stabilisers off. So scaffolding has to come down. That's one of Rosenshine's kind of key ideas, that we need to be clear that eventually the scaffolding comes off. Otherwise, the students are inhibited from really gaining that level of independent knowledge.